There is a star so impossibly large that if you placed it where our Sun sits, its surface would extend past Saturn's orbit, swallowing Mercury, Venus, Earth, Mars, Jupiter and Saturn whole. Light itself, travelling at 670 million miles per hour, requires over 8 hours just to circle this cosmic titan once. Stephenson 218 is not merely big. It is a violation of everything our intuition tells us about how large objects in space should be. With a volume 10 billion times greater than our Sun, this dying red supergiant burns with the fury of 440,000 suns combined. Scientists only confirmed its true size in recent years, and what they found challenges our understanding of stellar physics itself. We are about to journey inside the largest known star in the observable universe. If you enjoy journeys that shatter your understanding of cosmic scales, hit that like button and subscribe. We are about to witness something that will fundamentally change how you see every star in the night sky. Let's begin. The year was 2012, when astronomers first realized something extraordinary lurked within a dense star cluster near the heart of our galaxy. Buried behind thick curtains of interstellar dust, hidden from optical telescopes for centuries, a star of almost incomprehensible proportions was about to reveal itself to human observers. That star would eventually earn recognition as the largest known stellar object in the observable universe. Its name carries the clinical precision of scientific nomenclature. Stephenson 218. But there is nothing clinical about what this designation represents. Deep within the constellation Scutum, roughly 20,000 light-years from Earth, exists a cluster of red supergiant stars that astronomers call Stephenson 2. This cluster was first catalogued by American astronomer Charles Bruce Stephenson in 1990, appearing in his work surveying infrared sources across the Milky Way. At the time, nobody understood what monsters lurked within this stellar grouping. The technology simply did not exist to penetrate the cosmic dust and measure what lay beyond. Stephenson was mapping the galaxy systematically, documenting bright infrared sources without any way to determine their true physical nature. His catalogue entry for this particular cluster represented just another data point among thousands. The constellation Scutum itself holds significance in this story. Located in a region of sky that gazes toward the inner spiral arms of our galaxy, Scutum contains some of the densest star fields visible from Earth. The Milky Way appears thickest and brightest when you look toward this part of the sky during summer months, yet this apparent richness conceals an even greater richness hidden behind veils of cosmic dust that block visible light from the most distant stellar populations. Stephenson 2 contains at least 26 red supergiant stars, making it one of the most massive stellar clusters ever discovered in our galaxy. The sheer concentration of these dying giants in a single location makes this cluster extraordinary, even before considering the dimensions of its largest member. But among these giants, one star stands apart. Stephenson 218, sometimes called Stephenson 2 DFK1 in technical literature, dominates the cluster with dimensions that challenge the boundaries of stellar physics itself. To understand why this star matters, you first need to grasp how astronomers measure stellar sizes across distances that make direct observation impossible. We cannot simply point a ruler at a star 20,000 light-years away. The challenge resembles trying to measure the diameter of a coin located in a city on the opposite side of Earth using only a telescope. The angular size becomes so small that distinguishing any structure from a simple point of light requires extraordinary precision. Instead of direct measurement, scientists employ a combination of spectroscopy, parallax measurements, and sophisticated modelling to determine what they call angular diameter. This measurement describes how large a star appears from Earth, expressed in fractions of an arcsecond. The problem becomes immediately apparent when you consider scale. An arcsecond represents 1/3600th of a degree. To put this in perspective, the full moon spans about 1,800 arcseconds across. A human hair held at arm's length covers roughly 60 arcseconds. Stars at cosmic distances appear so small that their angular diameters measure in milliarcseconds or even microarcseconds, required the most advanced infrared interferometers ever constructed. But angular diameter means nothing without knowing distance. A nearby small star and a distant giant star can appear identical in size from Earth's perspective. Determining actual physical dimensions requires calculating how far away the object sits, then combining that distance with the angular measurement. This two-step process introduces uncertainty at each stage, compounding the difficulty of obtaining accurate size measurements for distant objects. For stars buried behind galactic dust clouds, the distance calculation becomes extraordinarily challenging. The primary method astronomers use, called parallax, relies on measuring how a star's apparent position shifts as Earth orbits the Sun. More distant stars show smaller shifts. By measuring this shift precisely, scientists can calculate distance using simple geometry. The Gaia Space Observatory, launched by the European Space Agency in 2013, revolutionized parallax measurements by tracking the positions of nearly 2 billion stars with unprecedented accuracy. Stephenson 218 sits in one of the most obscured regions of our galaxy. Between Earth and this stellar monster lies approximately 20 magnitudes of visual extinction. This technical term quantifies how much light the intervening dust absorbs and scatters. 20 magnitudes means that in visible light wavelengths, the star appears roughly 100 million times fainter than it would without intervening dust. To grasp this dimming, imagine trying to see a candle through a wall of fog 100 million times thicker than any fog that forms on Earth. Optical telescopes cannot see Stephenson 218 at all. The star is completely invisible to instruments operating in visible wavelengths. Only infrared observations, which penetrate dust clouds far more effectively, reveal this star's presence. The physics behind this penetration relates to how light interacts with dust particles. Dust grains in interstellar space measure roughly a micrometer across, comparable to the wavelength of visible light. When electromagnetic radiation encounters particles of similar size, scattering occurs efficiently. Shorter wavelengths scatter more than longer wavelengths, which is why our sky appears blue and sunsets appear red. Infrared light, with wavelengths several times longer than visible light, passes through dust clouds with far less scattering. The cosmic fog that renders Stephenson 218 invisible to optical telescopes becomes semi-transparent at infrared wavelengths. When astronomers finally combined infrared brightness measurements with careful distance calculations, using data from the Gaia Space Observatory and other sources, the numbers that emerged seemed almost impossible. Stephenson 218 measures approximately 2,150 solar radii in diameter. This figure comes with significant uncertainty, ranging perhaps from 1,800 to 2,400 solar radii, depending on measurement methodology. But even the conservative estimates place this star among the largest ever discovered. Let me translate that measurement into terms human minds might process, though I warn you that intuition will fail regardless. Our Sun measures roughly 865,000 miles across. This already exceeds human comprehension. You could line up 109 Earths across the Sun's diameter. The Sun contains enough volume to hold 1.3 million Earths inside it. By any terrestrial standard, our star is enormous. Written out fully, that number contains 10 digits. Light, the fastest thing in the universe, travelling at 670 million miles per hour, requires roughly 3 hours to travel that distance. The light leaving one side of this star right now will reach the opposite side before your next meal. Consider another comparison. A commercial airplane flying at 500 miles per hour would need over 400,000 years to cross this star's diameter. If such a flight had departed when modern humans first emerged in Africa, it would still have hundreds of thousands of years of travel remaining before reaching the opposite edge. The journey would span more generations than have ever existed in all of human history. But diameter alone fails to capture the true enormity. Volume scales with the cube of radius, meaning that when you double diameter, you increase volume by a factor of 8. When you increase diameter by 2,150 times, volume increases by nearly 10 billion times. When you calculate the volume of Stephenson 218 compared to our Sun, the ratio approaches 10 billion to 1. Nearly 10 billion suns could fit inside this single star with room to spare. The number defies meaningful comprehension. Here is another way to grasp this volume comparison. If our Sun were the size of a basketball, approximately 9.5 inches across, then Stephenson 218 would be a sphere roughly 1,700 feet in diameter. That exceeds the height of the Empire State Building. A basketball compared to a sphere taller than Manhattan's most famous skyscraper. That is the volume ratio between our star and the largest known star in the universe. Consider a more tangible spatial comparison. If you place Stephenson 218 at the center of our solar system, with its core where our Sun currently burns, its surface would extend outward, past the orbit of Saturn. Mercury would be gone, vaporized inside the stellar atmosphere, or simply swallowed by the star's interior. Venus would be gone. Earth and everyone who has ever lived would be gone. Mars and the robots we have sent there would be gone. The entire asteroid belt, containing millions of rocky fragments orbiting between Mars and Jupiter, would be gone. Jupiter, the largest planet in our solar system with enough mass to contain all other planets combined, would be gone along with its 79 known moons. Saturn, with its magnificent rings that span distances larger than Earth, would orbit just above the churning surface of this stellar monster, occasionally dipping into the star's outer atmosphere during the closest approaches in its elliptical path. Uranus and Neptune would survive, but they would orbit a sun that fills their entire sky. From Uranus, you would see a wall of dim red light stretching from horizon to horizon, covering half the celestial sphere. The outer solar system would be bathed in an eerie crimson glow, emanating from a star so vast that the concept of daytime would lose all meaning. Day and night, as we understand them, require a sun that occupies a small portion of the sky. When your sun fills half your visual field, the entire concept breaks down. The cluster housing this monster deserves attention in its own right. Stephenson 2 ranks among the most massive stellar clusters in the Milky Way, containing a total mass estimated between 40,000 and 100,000 solar masses. This mass exists in the form of perhaps several hundred stars of various sizes, plus associated gas and dust. The cluster spans roughly 6 light-years across, meaning light itself requires 6 years to travel from one edge to the other. Within this relatively compact region, some of the most extreme stars in our galaxy burn through their nuclear fuel at prodigious rates. To understand what 6 light-years means, consider that the nearest star to our Sun, Proxima Centauri, lies about 4.24 light-years away. The entire Stephenson 2 cluster would fit comfortably in the space between our solar system and our nearest stellar neighbour. Yet within this volume, 26 red supergiants and dozens of smaller stars crowd together, each one potentially destabilized by gravitational interactions with neighbours. Why does this cluster contain so many red supergiants simultaneously? The answer lies in stellar evolution and the timing of observations. Massive stars live fast and die young by cosmic standards. While our Sun will burn hydrogen for approximately 10 billion years, a star 20 times more massive exhausts its hydrogen in merely 10 million years. The most massive stars in Stephenson 2 likely formed roughly 20 million years ago during a burst of star formation, triggered by some unknown cosmic event, perhaps a passing gas cloud compression, or the shockwave from a nearby supernova. Those original stars that weighed in at perhaps 20 to 40 solar masses have now evolved off the main sequence. Their hydrogen fuel exhausted, their cores contracting while their outer layers expand to monstrous proportions. We are witnessing Stephenson 2 during a brief window when its most massive members have become red supergiants but have not yet exploded as supernovae. In another million years, perhaps less, many of these giants will have detonated, leaving behind neutron stars or black holes. The cluster we observe today represents a snapshot of stellar evolution caught at the perfect moment. This timing dependence means that clusters containing multiple red supergiants are inherently rare. The red supergiant phase lasts only a few 100,000 years, a cosmic eye blink compared to total stellar lifetimes. Finding 26 such stars in one location requires observing a cluster during precisely the right epoch. Stephenson 2 provides a laboratory for studying this crucial evolutionary phase, with multiple examples of red supergiants available for comparison within a single gravitationally bound system. The discovery timeline for Stephenson 218 reveals how technology drives astronomical progress. Charles Bruce Stephenson's original catalogue from 1990 simply noted bright infrared sources detected during systematic surveys. He lacked the tools to determine physical properties like size, mass, or temperature. His observations used early infrared detectors with limited sensitivity and resolution compared to modern instruments. Through the 1990s and 2000s, various surveys added information piece by piece. The 2-micron all-sky survey, completed in 2001, provided improved infrared measurements for millions of sources, including stars in the Stephenson 2 cluster. The Spitzer Space Telescope, launched in 2003, revealed additional details about the cluster environment through observations at mid-infrared wavelengths inaccessible from Earth's surface. But precise size measurements required combining multiple data sources in ways that became possible only in the 2010s. The Gaia mission, launched in 2013, provided revolutionary distance measurements using parallax observations repeated over years of spacecraft operation. Ground-based infrared interferometers achieved angular resolution, sufficient to constrain stellar diameters for even distant objects. Sophisticated atmospheric models developed by theoretical astrophysicists allowed astronomers to connect observed brightness and temperature to physical size through established physical relationships. The convergence of these capabilities produced the modern understanding of Stephenson 218 as the largest known star, but this understanding comes with important caveats that reveal how much uncertainty remains in measuring extreme cosmic objects. Stellar size measurements carry significant error bars, often ranging 20 to 30% or more for distant objects obscured by dust. Different research groups using different methodologies arrive at different conclusions. Some measurements of Stephenson 218 suggest dimensions exceeding 2,400 solar radii, which would make it even more impossibly large. Others cluster around 1,800 to 2,000 solar radii, still enormous, but slightly less extreme than the central estimate. The scientific consensus accepts values in the 2,000 to 2,200 range, but researchers continue refining measurements as techniques improve. The variability of red supergiants compounds this uncertainty in ways that challenge the very concept of stellar size. These stars pulsate, expanding and contracting over periods lasting hundreds or thousands of days. A red supergiant observed at maximum expansion may appear significantly larger than the same star observed months later at minimum size. For Stephenson 218, pulsation periods probably span several years, meaning comprehensive observations require patient monitoring over extended timescales. Their outer atmospheres lack well-defined edges, instead fading gradually from dense stellar material into thin circumstellar envelopes that blend into interstellar space. Where exactly does the star end and space begin? The boundary depends entirely on how you define stellar surface. Astronomers typically use what they call the photosphere as the defining boundary. This represents the depth at which the star becomes opaque to radiation, where light can no longer escape freely into space. But for red supergiants, the photosphere can be extraordinarily diffuse, more resembling a thick fog than a solid surface. Defining size becomes somewhat arbitrary when the object itself lacks clear boundaries. Despite these complications, the evidence overwhelmingly supports Stephenson 218 as the current record holder for largest known star. Multiple independent measurements using different techniques converge on dimensions exceeding 2,000 solar radii. While the precise figure remains uncertain, the basic fact stands confirmed. This star is larger than anything else we have found in the observable universe. The location of this stellar monster matters for understanding why it remained hidden for so long. Stephenson 2 sits in a direction that looks toward the inner regions of our galaxy, where dust concentrations reach their highest levels. The line of sight passes through multiple spiral arms, each adding layers of obscuring material between Earth and the cluster. The Scutum Centaurus arm, the nearest major spiral arm interior to our own, contributes particularly heavy extinction. Additional dust lanes associated with the galactic bar and the inner molecular zone further obstruct the view. This same dust that hid Stephenson 218 also shields it from the energetic radiation permeating denser galactic regions. High-energy photons from the galactic center, cosmic rays accelerated by supernova remnants, ultraviolet radiation from hot young stars in the inner galaxy, all of these potentially destructive influences are absorbed by the same material that blocks our view. The cluster exists in a relatively protected environment, which may have allowed its stars to evolve without external disruptions. Supernovae from nearby stars, intense radiation from the galactic core, gravitational perturbations from passing objects. All of these could have altered the cluster's evolution. Instead, Stephenson 2 appears to have developed in relative isolation, following its own internal evolutionary trajectory. The infrared wavelengths that finally revealed this star operate according to different physics than visible light. Dust particles scatter and absorb visible light very effectively because dust grain sizes are comparable to visible wavelengths. But infrared light, with wavelengths ranging from 1 to hundreds of micrometers, interacts far less strongly with the same dust particles. The mathematical relationship between wavelength and scattering efficiency means that light at 2 micrometers wavelength penetrates dust roughly 10 times more effectively than light at half a micrometer in the blue portion of the visible spectrum. This principle drives modern surveys of obscured galactic regions. Telescopes, sensitive to infrared wavelengths, see through cosmic dust like X-rays see through human flesh. The 2-micron all-sky survey, the Wide-Field Infrared Survey Explorer, the Spitzer Space Telescope, and ground-based infrared observatories have revealed entire populations of stars invisible to optical instruments. Hundreds of millions of stars exist in our galaxy that no optical telescope will ever detect because the intervening dust is simply too thick. Stephenson 218 represents one particularly spectacular example of what infrared astronomy reveals. Stephenson 218 shines brightest at wavelengths around 2 micrometers, deep in the infrared spectrum. At these wavelengths, the dust that blocks 99.9999% of its visible light blocks only a small fraction of its infrared emission. The star that appears utterly invisible through an optical telescope becomes one of the brightest sources in the infrared sky at its particular wavelength. This dramatic difference in apparent brightness between optical and infrared observations immediately flags the object as interesting, worthy of detailed follow-up study. The temperature of Stephenson 218 explains why it peaks in the infrared rather than at visible wavelengths. All objects emit thermal radiation, with a spectrum determined by their temperature. Hotter objects emit radiation at shorter wavelengths, peaking in the blue or ultraviolet. Cooler objects emit radiation at longer wavelengths, peaking in the infrared or beyond. Red supergiants have surface temperatures ranging from 3000 to 4000 Kelvin, cool by stellar standards. Our Sun's surface reaches 5778 Kelvin. Blue supergiant stars exceed 20,000 Kelvin. The cooler temperature of red supergiants shifts their peak emission toward longer wavelengths, making them naturally infrared bright objects regardless of any intervening dust. But cool temperature combined with enormous size produces tremendous luminosity through a fundamental physical relationship called the Stefan-Boltzmann law. This law describes how brightness depends on both temperature and surface area. The total energy radiated scales with temperature to the fourth power and with surface area directly. While Stephenson 218 radiates less energy per square meter than our Sun due to its cooler surface, it has vastly more surface area. The ratio of surface areas exceeds 4 million to 1. The net effect produces luminosity estimates ranging from 440,000 to 630,000 times our Sun's output. This luminosity figure deserves careful consideration because it seems paradoxical. Stephenson 218 pours out energy equivalent to hundreds of thousands of suns combined. Yet this energy spreads across a surface area billions of times larger than our star. The result is a surface brightness that appears surprisingly dim despite the enormous total output. Standing on a hypothetical planet near this star, you would see a vast red wall filling your sky, but the surface brightness of that wall would be lower than our Sun's surface brightness. Each square meter of Stephenson 218 emits less light than each square meter of our Sun. The star appears red and relatively cool despite its enormous total energy output, because that output spreads so thin across such vast area. The sheer scale creates phenomena unknown in smaller stars. Sound waves in stellar material travel at speeds determined by temperature and density. In the tenuous outer layers of Stephenson 218, sound moves at roughly a few kilometers per second. Given the star's immense diameter, acoustic waves would take weeks to travel from one side to the other. Signals that propagate through the stellar interior cannot coordinate the behavior of distant regions on any timescale relevant to human observation. The story of Stephenson 218 illustrates a broader truth about astronomical discovery. The universe contains objects so extreme, so far beyond ordinary experience, that finding them requires technologies our ancestors could never imagine. Each generation of telescopes reveals wonders invisible to previous generations. Each advance in sensitivity and resolution expands our catalogue of cosmic extremes. The astronomers of the 19th century could not have conceived of a star this large because they lacked the tools to detect it and the theoretical framework to understand it. We have found the largest known star in the observable universe. But the qualifier known matters enormously. The Milky Way contains roughly 400 billion stars. We have characterized the sizes of only a tiny fraction, perhaps a few thousand stars with sufficient precision to place them in size rankings. Somewhere in the unexplored regions of our galaxy, perhaps behind even thicker dust clouds, perhaps in clusters not yet surveyed, larger stars might wait for discovery. The current record could fall next year or stand for centuries. We cannot know until we look. For now, Stephenson 218 holds the crown. A star so vast that planetary systems could orbit within its atmosphere. A star so luminous that it outshines hundreds of thousands of suns combined. A star so extreme that its existence probes the fundamental limits of what stellar physics permits. The measurements are confirmed. The calculations are sound. The largest known star in the universe burns 20,000 light-years away. Invisible to human eyes but revealed through the patient work of astronomers who learn to see in infrared light. What they found challenges everything our intuition suggests about how large objects in space can grow. Stars do not begin their lives as red supergiants. Stephenson 218 started as something far more ordinary, a massive ball of hydrogen collapsing under its own gravity, destined to spend most of its existence as a hot blue or blue-white star, burning with ferocious intensity. The transformation into the bloated monster we observe today required millions of years of nuclear alchemy, a process that converts hydrogen into helium, helium into carbon, carbon into oxygen, and eventually creates elements all the way up to iron in the periodic table. Each transformation releases energy, while bringing the star one step closer to catastrophic death. Understanding how Stephenson 218 became the largest known star requires tracing this evolutionary journey from stellar birth to impending destruction. The physics driving this transformation operates according to principles discovered over the past century. Yet applying these principles to extreme objects still challenges our most sophisticated models. Stars this large push theoretical frameworks to their breaking points. A star's fate depends almost entirely on one factor determined at birth: mass. The amount of material that collapses to form a star dictates how hot its core will burn, how quickly it will consume fuel, how long it will live, and what kind of remnant it will leave behind when nuclear fusion ceases. This determinism operates with ruthless precision. Know a star's initial mass, and you can predict its entire evolutionary trajectory with remarkable accuracy. Stephenson 218 began with an initial mass estimated between 25 and 40 solar masses, placing it among the most massive stars that form in our galaxy. To appreciate what this means, consider that stars containing more than 8 solar masses represent less than 1% of all stars born. Stars exceeding 20 solar masses are rarer still, perhaps 1 in 1,000. Stars approaching 40 solar masses sit at the extreme tail of the stellar mass distribution, so rare that astronomers must survey enormous volumes of space to find significant samples. This initial mass established the star's destiny from the moment hydrogen fusion ignited in its core. Every subsequent phase, the billions of years of stellar evolution compressed into mere millions, followed inevitably from that starting condition. Massive stars live fast and die young by cosmic standards. Our Sun, a relatively modest 1 solar mass star, will burn hydrogen for approximately 10 billion years before evolving into a red giant and eventually becoming a white dwarf. The Sun has already completed roughly half this journey, with another 5 billion years of stable hydrogen burning ahead. Stars like Stephenson 218 exhaust their hydrogen fuel in mere millions of years, perhaps 10 to 15 million years depending on exact initial mass. The physics behind this counterintuitive fact relates to how fusion rates depend on temperature and pressure. You might expect that a star with 30 times more fuel than the Sun would live 30 times longer. The opposite proves true. Massive stars burn through their reserves so rapidly that they live far shorter lives despite their greater fuel supply. More massive stars have stronger gravity, which compresses their cores to higher densities and temperatures. The core temperature of a star like Stephenson 218 during its main sequence phase exceeded 40 million Kelvin, roughly 3 times hotter than the Sun's core temperature of 15 million Kelvin. This temperature difference has enormous consequences, because nuclear fusion rates increase exponentially with temperature. The primary hydrogen fusion process in massive stars differs from the process operating in our Sun. While the Sun fuses hydrogen through the proton-proton chain, massive stars predominantly use the carbon-nitrogen-oxygen cycle, often abbreviated CNO cycle. This process employs carbon, nitrogen, and oxygen nuclei as catalysts, allowing hydrogen fusion to proceed at rates far exceeding the proton-proton chain. The CNO cycle rate scales approximately with the 16th power of temperature, meaning small temperature increases produce enormous rate increases. Double the stellar mass and the luminosity increases by roughly a factor of 10 or more, following what astronomers call the mass-luminosity relationship. The fuel supply increases proportionally with mass, but the consumption rate increases much faster due to the temperature sensitivity of nuclear reactions. Massive stars burn through their reserves at prodigious rates, squandering their inheritance in a cosmic eye blink. When Stephenson 218 first ignited hydrogen fusion in its core perhaps 20 million years ago, it shone as a brilliant blue supergiant. Surface temperatures exceeded 20,000 Kelvin, more than 3 times hotter than our Sun's surface. The star radiated primarily in ultraviolet wavelengths, invisible to human eyes but deadly to any unprotected life nearby. Planets orbiting within a light year of this young star would have been bathed in sterilizing radiation that would prevent any chemistry resembling terrestrial biology. Its luminosity already exceeded tens of thousands of suns during this early phase, making it visible across enormous distances, despite occupying a relatively small volume compared to its current dimensions. The young Stephenson 218 was a compact furnace, perhaps 10 to 20 times the Sun's diameter, but radiating energy at rates millions of times greater per unit volume. During this main sequence phase, lasting perhaps 12 million years, the star maintained equilibrium between two opposing forces locked in eternal combat. Gravity pulled material inward, attempting to collapse the star into its own center. Every particle in the star felt the gravitational attraction of every other particle, creating an inward pressure that would crush the object into oblivion if left unopposed. Radiation pressure from the nuclear furnace pushed outward, supporting the star against gravitational collapse. The nuclear reactions in the core released energy that traveled outward through the stellar interior, pushing against the infalling material. This outward pressure exactly balanced the inward gravitational force, creating what physicists call hydrostatic equilibrium. The balance persisted as long as hydrogen fuel remained available in the core to power the nuclear furnace. But hydrogen cannot last forever, no matter how vast the initial supply. The nuclear reactions that power stars convert hydrogen nuclei into helium nuclei, releasing energy through Einstein's famous equation E=m². Each fusion reaction converts 4 hydrogen nuclei into 1 helium nucleus, releasing the energy equivalent of the small mass difference between reactants and products. This mass difference, roughly 0.7% of the original hydrogen mass, transforms entirely into energy. The helium produced by hydrogen fusion accumulates in the core like ash building up in a fireplace. Unlike hydrogen, helium requires much higher temperatures to ignite, because helium nuclei carry greater positive charge and repel each other more strongly. Temperatures exceeding 100 million Kelvin are needed before helium nuclei can approach closely enough for the strong nuclear force to fuse them together. The star's core gradually transforms from nuclear reactor to inert ball of helium as the surrounding hydrogen depletes. This accumulation proceeds invisibly for millions of years. The core grows heavier with helium, while hydrogen burning continues in the shrinking region where hydrogen still exists. Eventually, the helium core contains enough mass that its weight becomes significant, its internal pressure increasing as it contracts under gravity while waiting for temperatures high enough to ignite its own nuclear fires. When hydrogen exhaustion occurs in the core, the delicate equilibrium breaks catastrophically. Without nuclear energy generation to support against gravity, the helium core contracts. There is no longer any energy source preventing gravitational collapse in the central regions. The core falls inward, compressing and heating, as gravitational potential energy converts to thermal energy. This contraction releases enormous amounts of gravitational energy, heating both the core and the surrounding layers. A shell of hydrogen just outside the core reaches temperatures sufficient for fusion, igniting a new nuclear burning zone in a thin layer surrounding the inert helium core. This shell burning phase marks the beginning of the star's transformation into a giant. The energy released by shell hydrogen fusion exceeds what the previous core fusion produced. This seems paradoxical since the shell contains less material than the original core, but the shell burns at higher temperatures and greater densities, accelerating reaction rates. The outer layers of the star respond to this increased energy flow by expanding outward against gravity. The star swells enormously, with its surface cooling as material spreads across ever larger volumes. This expansion represents a fundamental restructuring of stellar architecture. The compact hot blue star transforms into an extended, cool red object over timescales of thousands of years, brief by stellar standards but still lengthy compared to human experience. The surface retreats outward as the interior rearranges itself to accommodate the new energy generation pattern. For Stephenson 218, this expansion continued far beyond what occurs in ordinary stars. The physics driving extreme expansion relates to how energy transport occurs within stellar interiors. Understanding this transport mechanism explains why some stars become enormously bloated, while others remain relatively compact through similar evolutionary phases. In the deep core and surrounding regions, radiation carries energy outward as photons bounce repeatedly off dense material in a process called radiative diffusion. Each photon travels only a short distance before interacting with an electron or atomic nucleus, changing direction randomly. The journey from core to surface involves countless such interactions, with photons effectively random, walking through the stellar interior. In our Sun, this radiative diffusion requires roughly 170,000 years for energy generated in the core to reach the surface. But in the cooler outer regions of massive evolved stars, convection becomes more efficient than radiation for transporting energy. Giant cells of rising and sinking material transport energy like boiling water in a pot. Hot material rises from deeper layers, carries its heat to cooler regions above, then sinks back down after cooling. This convective transport moves energy far more efficiently than radiation in regions where the temperature gradient becomes steep enough. The transition from radiative to convective energy transport affects stellar structure profoundly and explains why red supergiants become so enormously extended. Convective envelopes can expand nearly without limit if sufficient energy flows through them from below. The stellar surface retreats outward, cooling as it expands, eventually reaching temperatures where molecules can form in the outer atmosphere. The expansion continues until a new equilibrium establishes itself, with energy generated in the burning shells transported outward through the convective envelope and radiated into space from the cool, extended surface. For the most massive stars, this equilibrium occurs at dimensions measured in thousands of solar radii. Convection in red supergiants operates on scales that dwarf anything in our solar system or any everyday experience. Individual convection cells can span several astronomical units, larger than the distance from Earth to the Sun. 1 astronomical unit equals roughly 93 million miles, the average distance from Earth to the Sun. Convection cells on Stephenson 2.18 probably span distances larger than Jupiter's orbit, which lies over 5 astronomical units from the Sun. These massive convection cells appear as bright and dark patches on resolved images of nearby red supergiants. The bright patches represent hot material rising from below. The dark patches represent cooler material sinking back into the interior. The contrast between rising and sinking regions creates a mottled, uneven surface that changes configuration over timescales of months to years. Observing these convection patterns directly on Stephenson 2.18 remains impossible due to the great distance and intervening dust, but observations of closer red supergiants like Betelgeuse reveal exactly this kind of large-scale surface structure. Betelgeuse, located only about 700 light-years from Earth, shows convection cells roughly the size of Earth's orbit when observed with advanced imaging techniques. Stephenson 2.18 almost certainly displays similar features on even grander scales. At the current stage observed by astronomers, Stephenson 2.18 has completed core hydrogen burning long ago. The helium core contracted and heated until helium fusion ignited, converting helium into carbon and oxygen through what nuclear physicists call the triple alpha process. This process requires 3 helium nuclei to combine almost simultaneously into a carbon nucleus, an extremely unlikely event that requires very specific temperature and density conditions. The name triple alpha refers to the alpha particles involved, where alpha particle is the physics term for a helium nucleus containing 2 protons and 2 neutrons. 2 helium nuclei first combine briefly into an unstable beryllium-8 nucleus that normally decays back into 2 helium nuclei within a tiny fraction of a second. But at sufficient temperatures and densities, a 3rd helium nucleus can strike this short-lived beryllium before it decays, forming stable carbon-12. This reaction rate is exquisitely sensitive to temperature. Core temperatures must exceed 100 million Kelvin for helium burning to proceed at rates sufficient to support the star. Helium fusion produces less energy per unit mass than hydrogen fusion, meaning this phase proceeds more quickly than the main sequence. The helium burns away over perhaps 1 million years in a star like Stephenson 2.18, leaving behind a carbon-oxygen core that contracts further under gravity. The star now has a helium-burning shell surrounding an inert carbon-oxygen core with a hydrogen-burning shell farther out. and the vast convective envelope extending to the distant photosphere. In sufficiently massive stars like Stephenson 218, even carbon can ignite when core temperatures reach roughly 500 million Kelvin. Carbon nuclei fuse into neon, magnesium, and other heavier elements through reactions, releasing neutrinos along with electromagnetic energy. These neutrinos escape immediately from the star, carrying away energy without heating the surrounding material. This onion layer structure builds progressively over time. Each successive burning phase occurs at higher temperatures in an ever smaller core, surrounded by shells burning lighter elements. The star develops concentric layers like an onion, with iron and other heavy elements near the center, surrounded by silicon, then oxygen, neon, carbon, helium, and hydrogen shells extending outward through the envelope. The timescales for these advanced burning phases compress dramatically as heavier elements fuse. Carbon burning takes perhaps 1,000 years. Neon burning takes just a few years. Oxygen burning lasts mere months. Silicon burning, the final stage before catastrophe, completes in mere days. The star races through these phases with increasing desperation, burning ever heavier elements in a futile attempt to generate the energy needed to support against gravitational collapse. Stephenson 218 currently burns through these advanced stages deep in its core, while its enormous envelope remains largely unaware of the drama unfolding below. The outer layers respond to events in the core on timescales measured by the sound crossing time, the time required for pressure waves to travel from center to surface. For a star this size, that timescale measures in years or even decades. The surface we observe today reflects conditions in the core from years ago. The information about the current core state has not yet reached the photosphere. This communication delay means the extended envelope is effectively isolated from the core. The outer layers maintain their structure based on energy flow from deep interior regions, responding slowly to changes occurring far below. The star operates as a loosely coupled system, where different regions evolve quasi-independently on different timescales. The strange properties of red supergiant atmospheres deserve particular attention because they differ fundamentally from anything in human experience, or even from smaller stars like our Sun. At the photosphere of Stephenson 218, temperatures hover around 3,200 Kelvin. This is hot enough to glow visibly red, but cool enough for simple molecules to form despite the stellar environment. Spectroscopic observations detect titanium oxide, water vapor, and carbon monoxide molecules in the outer atmosphere of red supergiants. These molecules would be instantly destroyed in our Sun's 5,778-degree surface, where temperatures prevent stable molecular bonds. The cool temperatures of red supergiant photospheres allow chemistry to operate in ways impossible for smaller, hotter stars. These molecules affect how light escapes from the star, creating absorption features in the spectrum that allow astronomers to measure stellar properties. The molecular bands, particularly titanium oxide, give red supergiants their characteristic color and spectral appearance. Without these molecules, the stars would appear differently and would be more difficult to characterize. The density at the photosphere defies terrestrial intuition. While the core of Stephenson 218 remains far denser than any material on Earth, with densities approaching that of atomic nuclei in the innermost regions, the outer layers expand to extraordinarily low densities. At the visible surface, densities drop to roughly 1/1000th of Earth's atmospheric density at sea level. To put this in perspective, the outer atmosphere of Stephenson 218 qualifies as a better vacuum than most laboratory equipment on Earth can produce. High vacuum chambers used for scientific experiments typically achieve densities millions of times higher than the photospheric density of this star. The tenuous material forming the visible surface would be considered empty space by any practical terrestrial definition. Yet this incredibly diffuse material produces the light we observe. Photons generated in deeper, denser regions scatter and absorb through this extended atmosphere, before finally escaping into space. The long path through tenuous material allows even weak absorption processes to affect the emerging radiation significantly. The characteristic red color comes not from thermal radiation alone, but from complex absorption by molecules and atoms in these cool outer layers. The pulsation of red supergiants adds another layer of complexity to their already strange nature. These stars do not maintain constant sizes, but oscillate over periods ranging from hundreds to thousands of days. The star breathes in and out like a cosmic lung, expanding and contracting with remarkable regularity, considering the chaotic internal conditions. The pulsation mechanism relates to how opacity changes with temperature in the outer layers. Opacity describes how effectively material blocks radiation. As the star compresses, it heats slightly, changing how effectively material absorbs radiation. In certain temperature ranges, compression increases opacity, which traps more radiation, which increases pressure, which drives further expansion. The expansion leads to cooling, which decreases opacity, which allows radiation to escape, which decreases pressure, which allows contraction to begin again. This opacity-driven instability creates the regular pulsation observed in red supergiants and their smaller cousins, the mirror variable stars. The physics resembles the operation of a heat engine, with opacity playing the role of a valve that alternately traps and releases energy. For Stephenson 218, pulsation periods probably span several years based on the star's enormous dimensions and low density. During maximum expansion, the star might exceed 2,200 solar radii. During minimum, it might shrink below 2,000 solar radii. This represents a variation of 10% or more in radius, corresponding to more than 30% variation in volume. Mass loss from red supergiants proceeds through multiple mechanisms operating simultaneously and interacting in complex ways. Radiation pressure accelerates dust grains that form in the cool outer atmosphere. When temperatures drop below roughly 1,500 Kelvin in the extended envelope, silicate and carbon-rich dust grains can condense from the gas phase. These grains absorb starlight efficiently and experience strong radiation pressure that accelerates them outward. The accelerating dust grains drag gas along with them through collisions, creating stellar winds that carry material away from the star. This dust-driven wind mechanism operates continuously, steadily eroding the stellar envelope over thousands of years. The mass loss rate depends on how much dust forms, which depends on temperature, chemistry, and dynamics in the extended atmosphere. Pulsation drives shocks through the outer layers, ejecting material episodically rather than continuously. When the star compresses during its pulsation cycle, the compression propagates outward as a wave. This wave steepens into a shock as it travels through the decreasing density profile of the outer atmosphere. The shock accelerates material to velocities exceeding the local escape velocity, launching discrete shells of gas into space. Convective motions can lift material to heights where it escapes gravitational binding through yet another mechanism. The enormous convection cells transport material upward to the outer atmosphere, where it finds itself in regions of weaker gravitational binding. Given the extremely low surface gravity of red supergiants, material does not need much additional velocity to escape. The surface gravity of Stephenson 218 is perhaps 100,000 times weaker than Earth's surface gravity, making escape relatively easy for material that reaches the outer atmosphere. The combined effect of these mechanisms produces mass loss rates millions of times greater than our Sun's solar wind. The solar wind carries roughly 1 million tons of material away from the Sun every second. Stephenson 218 probably loses the equivalent of the Sun's total mass every few thousand to 10,000 years. This rate exceeds the solar wind by factors of billions. Over the remaining lifetime of this star, perhaps a few 100,000 years at most before core collapse triggers supernova explosion, it will shed several solar masses into surrounding space. The material leaving the star today will travel outward at roughly 10 to 30 kilometers per second. This ejected material creates circumstellar structures that provide evidence of the star's recent evolutionary history. Shells of previously ejected material surround Stephenson 2-18 at various distances, glowing faintly in infrared light as dust grains absorb stellar radiation and re-emit at longer wavelengths. Each shell represents a particular epoch of mass loss, frozen at the distance it has reached since ejection. Episodes of enhanced mass loss appear as denser shells. Periods of reduced mass loss appear as gaps between shells. The distribution of circumstellar material encodes information about how the mass loss rate has varied over tens of thousands of years. The comparison with other giant stars reveals where Stephenson 2-18 fits within the extreme stellar population, and why astronomers accept it as the current record holder. The contest for largest known star has a history spanning decades as measurement techniques improved and different objects took the lead. Before Stephenson 2-18 gained recognition, several other red supergiants held or competed for this distinction. Scuti, located about 5,700 light-years from Earth in the constellation Scutum near Stephenson 2 itself, was long considered a top contender. Early measurements suggested dimensions approaching 2,000 solar radii, potentially rivaling or exceeding Stephenson 2-18, but subsequent observations revised Scuti's size downward significantly. Improved distance measurements from the Gaia spacecraft suggested the star lies somewhat closer than originally thought, which reduces calculated physical dimensions when combined with angular size measurements. Current estimates place Scuti around 1,700 solar radii, still enormous but clearly smaller than Stephenson 2-18. VY Canis Majoris represents perhaps the most famous red supergiant, having held the record for largest known star through much of the early 2000s. This star dominates popular science discussions of stellar extremes, appearing in countless documentaries and educational materials. Located approximately 3,900 light-years away, VY Canis Majoris displays spectacular circumstellar structures created by its intense mass loss. However, size estimates for VY Canis Majoris have proven contentious, with values ranging from 1,400 to possibly 2,000 solar radii, depending on methodology. The star's complex circumstellar environment and unusual characteristics complicate measurements. Most recent comprehensive analyses place VY Canis Majoris around 1,400 to 1,500 solar radii, clearly smaller than the central estimates for Stephenson 2-18. What distinguishes Stephenson 2-18 from these competitors? The primary difference lies in converging measurements that place this star consistently above 2,000 solar radii, while other candidates show more uncertainty or lower central estimates. Multiple research groups using different techniques and data sources arrive at similar conclusions about Stephenson 2-18's exceptional dimensions. The star NML Cygni represents another competitor still debated among specialists. Located approximately 5,300 light-years away in the constellation Cygnus, NML Cygni displays properties suggesting dimensions possibly comparable to Stephenson 2-18. Some measurements hint at radii approaching 2,000 solar radii, though uncertainties remain large. The debate over which star truly holds the record continues in technical literature, but Stephenson 2-18 consistently appears at or near the top in comprehensive comparisons. Red supergiants as a class represent the final evolutionary stage for massive stars before catastrophic death. They are not simply large versions of ordinary stars, but physically distinct objects operating under different physics in many respects. The same fundamental equations of stellar structure govern all stars, yet the solutions describing red supergiants look nothing like those describing main sequence stars. The density contrast within red supergiants captures this fundamental strangeness. Objects larger than the orbit of Saturn somehow weigh less per unit volume than the air you breathe when averaged across their entire extent. This seeming impossibility arises from how stellar structure distributes mass. The dense core containing the nuclear burning regions occupies only a tiny fraction of the total volume. The vast extended envelope that defines the visible star contains relatively little mass, spread incredibly thin. Consider the average density comparison directly. Stephenson 2-18 contains perhaps 15 to 25 solar masses depending on how much material mass loss is removed. This mass occupies a volume roughly 10 billion times larger than the Sun. The average density therefore falls roughly 10 billion times below the Sun's average density. Our Sun has an average density of approximately 1.4 grams per cubic centimetre, slightly denser than water. Dividing by 10 billion gives an average density for Stephenson 2-18 of roughly 1/10 of a gram per cubic centimetre. This is far less dense than the best vacuums achievable in terrestrial laboratories. For comparison, Earth's atmosphere at sea level has a density of about 1/1000 of a gram per cubic centimetre. The average density inside Stephenson 2-18 falls roughly 10 million times lower than sea level air. A cubic metre of material from the average region of this star would contain less matter than a cubic metre of interplanetary space in our solar system. Of course, this average obscures enormous variation. The core remains extremely dense, with central regions approaching nuclear densities where matter behaves according to quantum mechanical rules quite different from ordinary materials. But the outer atmosphere, where we measure the star's visible boundary, is essentially empty space by any practical definition. This density structure creates the vast dimensions that make Stephenson 2-18 the record holder. The relatively modest total mass spreads across such enormous volume that average density plummets to nearly nothing. The star maintains this extended configuration through continuous energy flow from the nuclear burning regions, which supports the tenuous envelope against gravitational collapse. The physics allowing such extreme dimensions relates to how gravitational binding energy compares to thermal energy at different radii within the star. In the outer layers, thermal energy exceeds gravitational binding energy only marginally. The escape velocity from the surface of Stephenson 2-18 is perhaps 20 to 30 kilometers per second, compared to over 600 kilometers per second from our Sun's surface. The star maintains its enormous envelope through continuous adjustments rather than stable equilibrium. Energy flows outward from the burning shells, heating the envelope and preventing collapse. Mass flows outward through the stellar wind, gradually reducing the envelope mass. Pulsation drives oscillations that move material back and forth, occasionally ejecting portions into space. The system exists in a state of dynamic quasi-equilibrium, constantly adjusting but maintaining overall structure over timescales of thousands of years. Despite these challenges, the basic picture of how Stephenson 2-18 reached its current state seems well established in its broad outlines. A massive star formed roughly 20 million years ago, when a molecular cloud collapsed under its own gravity. The star burned through hydrogen in its core over 10 to 15 million years, while appearing as a hot blue supergiant. Shell burning triggered expansion into a red supergiant phase, lasting perhaps 100,000 years or less. The star continues evolving toward inevitable supernova explosion, while we observe it during this fleeting moment of maximum extension. What remains certain is the remarkable nature of the object. Stephenson 2-18 represents stellar evolution, pushed to extremes, the same physics that governs our modest sun producing under different initial conditions. An object so vast that comprehending its true nature requires abandoning all terrestrial intuitions about size, density, and structure. The largest known star in the universe exists not as a stable endpoint, but as a brief transitional phase in the life cycle of a massive star. We observe it during a window, lasting perhaps 100,000 years out of a total lifetime of 20 million years, less than 1% of the star's existence. Future observers will see Stephenson 2-18 only, in the aftermath of its explosive death. We are privileged to witness it during this fleeting moment when stellar dimensions reach their maximum possible extent before the core collapses and everything changes. Every red supergiant is a dying star. The bloated dimensions and cool red surface that define this stellar class represent symptoms of impending catastrophe, not stable characteristics of a healthy stellar object. Deep within Stephenson 218, nuclear processes are racing toward an inevitable endpoint that will transform this cosmic giant into something utterly different. The death of the largest known star will produce one of the most violent events possible in our universe, an explosion so energetic that it defies comparison with anything in human experience. The timeline ticks relentlessly forward with each passing second. Somewhere in the core of Stephenson 218, nuclear fusion converts silicon into iron at rates measured in days rather than the millions of years that characterized earlier burning phases. Or perhaps this final stage has not yet begun and the star still burns through oxygen or neon in its core. Or perhaps silicon burning has already completed and the core is collapsing at this very moment, though the signal of that collapse has not yet reached the surface, let alone travelled the 20,000 light-years to Earth. We cannot know the precise evolutionary state because looking into stellar cores requires detecting particles that travel at nearly light speed, and even those particles take years to reach us from this distant star. The information we receive today tells us about conditions 20,000 years ago. The star's current status remains forever hidden behind the finite speed of light, a cosmic uncertainty that applies to every distant object we observe. What we do know with confidence is that core collapse supernovae follow predictable physics once the iron core grows sufficiently massive. Iron represents the endpoint of stellar nucleosynthesis for a fundamental reason rooted in nuclear physics itself. Every element lighter than iron releases energy when fused into heavier elements. This energy release powers stars through their entire lives, from hydrogen burning on the main sequence through helium, carbon, neon, oxygen, and silicon burning in evolved massive stars. The energy comes from the difference in nuclear binding energy between reactants and products. Lighter nuclei are less tightly bound than intermediate mass nuclei, so combining them releases the difference as usable energy. Iron sits at the peak of the nuclear binding energy curve. Iron 56, the most common iron isotope, has the highest binding energy per nucleon of any element. This means that fusing iron into heavier elements does not release energy. The star cannot generate power by fusing iron any more than you can roll a ball uphill and extract energy from the process. The iron core is nuclear ash, the final waste product of stellar fusion, incapable of providing the energy needed to support the star against its own gravity. Every gram of iron that accumulates in the core represents material that will never again contribute to holding up the star. The core grows heavier while contributing nothing to the star's energy budget. Silicon burning deposits fresh iron into the core at prodigious rates during the final days of a massive star's life. The silicon burning phase lasts roughly 1 to 2 days, converting the silicon-rich shell surrounding the core into iron group elements. Each day adds roughly 1/10 of a solar mass to the iron core. The core grows like a tumor, absorbing energy rather than producing it. When the iron mass exceeds roughly 1.4 solar masses, a threshold called the Chandrasekhar limit after the physicist who calculated it, electron degeneracy pressure can no longer support the core against gravitational collapse. This limit represents a fundamental boundary in physics, where quantum mechanical effects that normally prevent matter from compressing indefinitely finally fail against overwhelming gravitational force. Electron degeneracy pressure arises from the Pauli exclusion principle, which forbids 2 electrons from occupying the same quantum state. In normal matter, this restriction limits how tightly electrons can pack together. But above the Chandrasekhar limit, gravity becomes strong enough to force electrons and protons together, converting them into neutrons and removing the electrons that provided the degeneracy pressure. The support vanishes catastrophically. What happens next unfolds with terrifying speed, compressing events that would normally require astronomical timescales into fractions of a second. The core implodes. Material falls inward at roughly 1/4 the speed of light, approximately 75,000 kilometers per second. The density increases by factors of trillions within less than a second, as the core compresses from roughly Earth-sized dimensions to a sphere perhaps 20 kilometers across. To grasp this compression, imagine squeezing Earth down to the size of a small city. All the mass remains, but the volume decreases by factors approaching 1 billion. The density in the collapsing core approaches and then exceeds the density of atomic nuclei themselves, roughly 200 trillion grams per cubic centimeter. A teaspoon of this material would weigh hundreds of millions of tons. During this collapse, protons and electrons merge to form neutrons through a process called electron capture or inverse beta decay. Each such reaction produces a neutrino, a nearly massless particle that interacts so weakly with matter that it typically passes through entire planets without stopping. The collapsing core releases enormous quantities of these ghostly particles, roughly 10 to the 58 individual neutrinos within a span of seconds. These neutrinos carry away the gravitational binding energy being released during collapse, more energy than the star has radiated as light throughout its entire lifetime of 20 million years combined. The neutrino luminosity during core collapse exceeds the combined light output of every star in the observable universe for a brief moment, yet these particles are so weakly interacting that most pass through the surrounding stellar envelope without depositing any energy at all. For Stephenson 218, the collapsing core probably contains between 1.5 and 3 solar masses of iron, depending on how much mass the star has lost through stellar winds over its red supergiant lifetime. The exact core mass determines critical aspects of the subsequent explosion and the nature of the remnant left behind. The initial implosion compresses this material from roughly Earth-sized dimensions to a sphere perhaps 12 to 15 miles across within about 1 second. Densities approach those found in atomic nuclei, where individual neutrons and protons touch each other directly. The strong nuclear force, which operates only at these incredibly short ranges, suddenly becomes relevant on macroscopic scales. What happens at the instant the core reaches nuclear density determines the explosive aftermath that will become visible to distant observers. Nuclear matter has a fundamental incompressibility. You cannot squeeze neutrons together beyond a certain point, because the strong force becomes repulsive at extremely short distances. This repulsion halts the collapse suddenly, like dropping a rubber ball onto concrete. The infalling material bounces off this newly formed neutron star core, creating an outward-moving shock wave. The bounce converts the kinetic energy of infall into the kinetic energy of outward expansion. This bounce shock carries enormous energy, roughly 10 to the 51 ergs, or about 1% of the total gravitational energy released. But the shock does not simply blast through the star and create the supernova we observe. Instead, it stalls. The overlying layers of the star absorb the shock's energy through nuclear dissociation, the breaking apart of heavy nuclei into their constituent protons and neutrons. Each iron nucleus that the shock encounters requires energy to disassemble, robbing the shock of momentum. Within roughly 100 milliseconds, the shock stalls at a radius of perhaps 100 to 200 kilometers, far short of the stellar surface. For decades, astronomers and physicists puzzled over how supernovae actually explode given this shock stalling problem. Computer simulations repeatedly showed the bounce shock dying before reaching the surface, leaving the star to collapse entirely into a black hole without any visible explosion. The observed supernovae clearly required some mechanism to revive the stalled shock. The answer involves those neutrinos released during neutron formation. Although neutrinos interact very weakly with matter, the densities in the region behind the stalled shock are so extreme that even weakly interacting particles deposit significant energy. Perhaps 1% of the outgoing neutrino flux gets absorbed in a layer just outside the nascent neutron star, heating this material and providing the energy needed to revive the shock. This neutrino heating mechanism remains an active area of research with many details still uncertain. Three-dimensional simulations suggest that turbulent convection and hydrodynamic instabilities play crucial roles, helping to channel neutrino energy into the shock revival process. The explosion mechanism appears far more complex than simple spherical models suggested, involving asymmetric flows and chaotic dynamics. Once revived, the shockwave resumes its outward journey through the stellar envelope. For a compact star like a blue supergiant, this journey requires only hours. For an enormously extended red supergiant like Stephenson 218, the shock must traverse nearly 2 billion miles of tenuous stellar material. Even travelling at thousands of kilometers per second, this journey requires many hours to complete. During this journey through the envelope, nuclear reactions in the shock-heated material synthesize heavy elements that cannot be made through normal stellar fusion. The extreme temperatures and densities behind the shock enable rapid neutron capture processes that build elements heavier than iron. Gold, platinum, uranium, thorium, and dozens of other heavy elements form in the extreme conditions behind the shock front. This nucleosynthesis contributes to the chemical evolution of the galaxy. The heavy elements ejected by supernovae mix with the interstellar medium and eventually become incorporated into new generations of stars and planets. Every atom of gold in jewelry, every atom of uranium in nuclear reactors, every atom of platinum in catalytic converters was synthesized in a supernova explosion and distributed across space by the resulting debris cloud. When the shock finally breaks through the surface of Stephenson 218, the supernova becomes visible to external observers. This shock breakout produces a brilliant flash as the shockwave suddenly encounters the tenuous outer atmosphere and accelerates material to extreme velocities. The star will brighten by factors of billions within hours, releasing radiation across the entire electromagnetic spectrum from radio waves through gamma rays. The shock breakout from a red supergiant differs dramatically from breakout in more compact progenitors. The extended, diffuse atmosphere of Stephenson 218 will produce a relatively gradual brightening as the shock propagates through the outer layers. This contrasts with the sharp, bright ultraviolet flash expected from blue supergiant explosions where the shock encounters denser material at the stellar surface. The peak luminosity of a supernova from a red supergiant like Stephenson 218 typically reaches several billion solar luminosities. For a period of days to weeks, this single exploding star will outshine every other star in its host galaxy combined. The Milky Way contains perhaps 400 billion stars, yet one dying red supergiant can temporarily produce more light than all of them together. From Earth, 20,000 light-years away, the supernova might briefly become visible to the naked eye, despite the intervening dust that currently hides the star from optical observation. The explosion energy will heat the surrounding dust, which will re-radiate at infrared wavelengths. This infrared brightening might actually appear more prominent than the optical emission due to the heavy extinction along the line of sight. The explosion will be classified as a Type II supernova based on the presence of hydrogen lines in its spectrum. The extended hydrogen-rich envelope of the red supergiant ensures that hydrogen dominates the outer ejector, producing characteristic spectral signatures that distinguish these explosions from Type I supernovae, occurring in stars that have lost their hydrogen envelopes. For Stephenson 218, the explosion energy will likely exceed 10 to the 44 joules, a unit astronomers call 1 Bethe, after physicist Hans Bethe, who contributed foundational work on stellar nucleosynthesis and supernova physics. This energy, released in seconds during the core collapse but distributed to the visible explosion over hours, equals roughly 1% of the total energy our Sun will radiate over its entire 10 billion year lifetime. Yet even this staggering output represents only about 1% of the total energy released during core collapse. The remaining 99% escapes as neutrinos, invisible to most detectors but potentially detectable by specialized facilities on Earth, if they happen to be operating and pointing in the appropriate direction. When supernova 1987A exploded in the Large Magellanic Cloud, roughly 168,000 light-years away, detectors worldwide registered a total of 25 neutrinos. 12 were captured by Kamiokande 2 in Japan, 8 by the IMB detector in the United States, and 5 by the Baksan detector in the Soviet Union. That detection, involving just a handful of particles from an extragalactic explosion, confirmed theoretical predictions about neutrino production in collapsing cores and earned a share of the 2002 Nobel Prize in Physics. For a galactic supernova like Stephenson 218 will eventually produce, modern detectors would register thousands or even tens of thousands of neutrino events over a span of roughly 10 seconds. The Super Kamiokande detector in Japan, the Ice Cube detector at the South Pole, and other neutrino observatories around the world would all record this flood of particles. The resulting data would provide unprecedented information about core collapse physics, including details about the neutron star formation, the explosion mechanism, and the properties of neutrinos themselves. The neutrino signal would arrive at Earth several hours before any electromagnetic radiation, because neutrinos escape the core immediately, while light must wait for the shock to reach the surface. This advance warning would allow astronomers to point telescopes toward the supernova before visible brightening begins, capturing the crucial early phases that are normally missed. The Supernova Early Warning System, an international network of neutrino detectors, exists specifically to provide this advance notification. The material ejected by the supernova will expand outward at velocities reaching 10,000 kilometers per second or more in the fastest moving layers. For comparison, the space shuttle orbited Earth at roughly 8 kilometers per second. The supernova ejector moved more than 1,000 times faster than any spacecraft humans have ever built. For a star as large as Stephenson 218, the ejector mass might reach 10 to 20 solar masses, depending on how much material the progenitor retained in its envelope prior to explosion. This material includes the hydrogen and helium layers that formed the extended red supergiant atmosphere, the products of nuclear burning in various shells, and the heavy elements synthesized during the explosion itself. The expanding debris will sweep through surrounding space at velocities that ensure it remains distinct from the ambient interstellar medium for thousands of years. The sharp boundary between fast-moving ejector and stationary surroundings creates a shock wave that heats material to temperatures of millions of degrees, producing X-ray emission detectable across vast distances. The enriched material from massive star supernovae provides the heavy elements necessary for rocky planets and biological chemistry. Every atom of oxygen you breathe was synthesized in a massive star through helium and carbon burning. Every atom of calcium in your bones, every atom of phosphorus in your DNA, every atom of copper in your neurons traces back to stellar nucleosynthesis and supernova distribution. The death of Stephenson 218 will seed surrounding space with the raw materials for future solar systems. In perhaps 1 billion years, material ejected by this explosion will have mixed with the interstellar medium and become incorporated into new molecular clouds. Those clouds will collapse to form new stars, some with planetary systems where the heavy elements from Stephenson 218 will become components of rocks, oceans, atmospheres, and perhaps even living organisms. This cosmic recycling connects us directly to stellar death. The carbon in your body, the oxygen in your lungs, the iron in your blood, all passed through stars that exploded before our solar system formed. You are made of stellar debris. The atoms comprising your body have histories spanning billions of years, processed through multiple stellar generations before assembling into the form you currently inhabit. The expanding supernova remnant will initially glow brightly as shock-heated material radiates energy through various physical processes. Free electrons spiraling in magnetic fields produce synchrotron radiation visible at radio wavelengths. Hot gas emits thermal X-rays as electrons collide with ions. Optical emission comes from specific atomic transitions as the gas cools and recombines. Over decades and centuries, this remnant will become visible as an expanding shell of gas similar to the Crab Nebula or Cassiopeia A, that we observe from historical supernovae in our galaxy. The Crab Nebula resulted from a supernova observed by Chinese astronomers in the year 1054. Nearly 1,000 years later, this remnant still spans roughly 11 light-years across and continues expanding at roughly 1,500 kilometers per second. Future astronomers, with sufficiently powerful telescopes, will watch the debris cloud from Stephenson 218 grow over centuries, mapping the distribution of ejected material and searching for clues about the explosion mechanism. The asymmetries and structures in the remnant will preserve information about the chaotic processes that occurred during the explosion itself. At the center of this expanding debris will sit the stellar remnant, the compressed core left behind after the explosion blasts away the outer layers. The exact nature of this remnant depends on the mass remaining in the collapsed core after the explosion, which in turn depends on complex dynamics that simulations struggle to predict precisely. If the remnant mass falls below roughly 2 to 3 solar masses, a neutron star will form. Neutron stars represent matter compressed to nuclear densities, supported against further collapse by neutron degeneracy pressure and the repulsive component of the strong nuclear force. These objects pack more mass than our Sun into spheres roughly 20 kilometers across, creating surface gravities billions of times stronger than Earth's. If a neutron star forms from Stephenson 218, it will be born spinning rapidly due to conservation of angular momentum during core collapse. The original massive star rotated slowly, perhaps once every few months. When the core collapses by factors of roughly 100,000 in radius, conservation of angular momentum increases the rotation rate by the same factor squared. The resulting neutron star might spin tens or hundreds of times per second initially. Young neutron stars also possess intense magnetic fields, typically 1 trillion times stronger than Earth's magnetic field. These fields form during core collapse through flux compression, as the magnetic field of the original star gets squeezed into a much smaller volume. The combination of rapid rotation and strong magnetic fields makes young neutron stars potentially observable as pulsars. Pulsars emit beams of radio waves along their magnetic axes, which are generally not aligned with their rotation axes. As the neutron star spins, these beams sweep across the sky like lighthouse beams. If Earth happens to lie in the path of the beam, we detect regular pulses of radio emission with the period of the neutron star's rotation. The pulsar at the center of the Crab Nebula, formed in the 1054 supernova, still pulses 30 times per second, nearly 1,000 years later. It has slowed from its original rotation rate due to energy losses from magnetic braking, but it remains one of the most energetic pulsars known. A neutron star from Stephenson 218 would likely show similar behavior, potentially detectable as a new pulsar within the expanding debris cloud. If the remnant mass exceeds roughly 2 to 3 solar masses, not even neutron degeneracy pressure can support it against further collapse. The core will continue compressing until it forms a black hole, an object so dense that not even light can escape its gravitational pull. For Stephenson 218, the outcome remains genuinely uncertain. The initial stellar mass suggested 25 to 40 solar masses. Mass loss through stellar winds during the red supergiant phase has removed significant material, perhaps reducing the current mass to 15 to 25 solar masses. The fraction of this mass that remains in the collapsed core depends on explosion dynamics and mass ejection that computer simulations struggle to predict precisely. The boundary between neutron star and black hole formation depends not only on the core mass, but also on the equation of state of nuclear matter at extreme densities. This equation of state remains incompletely understood, introducing uncertainty into predictions about remnant outcomes, even when progenitor properties are known. If a black hole forms instead of a neutron star, it will be initially invisible, except through its gravitational effects on surrounding material. Unlike neutron stars, black holes do not emit radiation directly. Any light or radio waves we might detect comes from material falling into the black hole, not from the black hole itself. Gas from the supernova ejector that fails to escape the vicinity will fall back toward the central remnant. If this material possesses sufficient angular momentum, it will form an accretion disk around the black hole. Friction within the disk heats the gas to extreme temperatures, producing X-ray emission detectable by orbiting observatories. The black hole mass might reach 5 to 15 solar masses, making it comparable to the black holes detected through gravitational wave observations by LIGO and Virgo. The gravitational wave signal from core collapse represents an active area of research distinct from the well-understood signals produced by compact object mergers. Unlike the clean chirp signals from merging black holes or neutron stars, core collapse produces more complex, stochastic gravitational wave emission, reflecting the turbulent, asymmetric dynamics of the explosion. Detectors like LIGO, Virgo, and CAGRA might detect gravitational waves from a galactic supernova, providing information about core dynamics completely inaccessible through electromagnetic observations. The gravitational waves originate from the collapsing core itself during the crucial seconds when the explosion develops, revealing processes hidden beneath the stellar envelope. The shock wave from the supernova will propagate through the Stephenson 2 cluster, potentially affecting the evolution of nearby stars. The radiation pulse will bathe neighboring red supergiants in intense ultraviolet and X-ray flux, possibly stripping material from their extended atmospheres. Any planets orbiting stars within the cluster would experience radiation doses lethal to surface life. The expanding debris cloud will eventually collide with gas and dust in the cluster environment, creating additional shock heating and possibly triggering new star formation. Supernovae can simultaneously destroy and create, their shocks compressing molecular clouds past the threshold of gravitational collapse, while enriching those clouds with heavy elements needed for planet formation. The supernova rate in Stephenson 2 depends on the masses and evolutionary states of its member stars. Given that the cluster contains over 20 red supergiants, all roughly the same age, and many with masses approaching the supernova threshold, multiple explosions should occur within the next few million years. Each explosion will reshape the cluster environment, enriching it with heavy elements while simultaneously disrupting any remaining star formation through the energy injection. The timeline for Stephenson 218's specific demise remains frustratingly uncertain despite our understanding of the physics involved. Red supergiants can persist for hundreds of thousands of years before core collapse, depending on their initial mass and mass loss history. The most massive evolve more quickly through advanced burning stages, potentially collapsing within tens of thousands of years after becoming red supergiants. Less massive stars in the red supergiant phase might persist for much longer. Observational indicators that might reveal the imminence of core collapse remain subjects of active research. Some theorists suggest that the final stages of nuclear burning should produce detectable changes in stellar properties, perhaps unusual variability, enhanced mass loss, or subtle spectral changes reflecting the changing interior conditions. But these predictions remain uncertain and have not been confirmed observationally. The red supergiant Betelgeuse in the constellation Orion underwent a dramatic dimming event in late 2019 and early 2020 that sparked widespread speculation about imminent supernova. The normally brilliant star faded to roughly 1/3 of its typical brightness, prompting headlines asking whether we were about to witness a stellar explosion in real time. Subsequent analysis attributed the dimming to a large dust cloud ejected by the star passing through our line of sight, combined with coincidental surface cooling during the star's regular pulsation cycle. Betelgeuse was not dying, merely sneezing. The star has since returned to normal brightness and will likely persist for another 100,000 years before exploding. The event demonstrated both public fascination with supernova predictions and the difficulty of making such predictions reliably. For Stephenson 218, the enormous distance and heavy dust obscuration prevent the detailed monitoring possible for closer stars like Betelgeuse. We cannot track subtle brightness variations that might signal changing interior conditions. We cannot obtain high-resolution spectra that might reveal compositional changes in the stellar wind. We cannot image the stellar surface to look for unusual convective patterns or mass ejection events. The supernova, when it occurs, will likely come as a complete surprise to astronomers on Earth. The first indication might be a flood of neutrinos registered by detectors worldwide, arriving several hours before any electromagnetic brightening becomes visible. Alternatively, we might detect the supernova through its infrared brightening, as the explosion heats surrounding dust, or through gravitational waves if detectors happen to be operating at sufficient sensitivity. The light from that supernova has perhaps already begun its 20,000-year journey toward Earth. The core of Stephenson 218 might have collapsed thousands of years ago, with the resulting explosion expanding outward through the stellar envelope, breaking through the surface, and sending photons racing toward distant observers. Those photons would currently be traveling through interstellar space, approaching our position at the speed of light, carrying news of an event that occurred before the earliest human civilizations developed writing. Alternatively, the core collapse might lie hundreds of thousands of years in the future, with the star continuing to burn through its remaining nuclear fuel in the sequence of increasingly rapid stages that characterize the final evolution of massive stars. The present-day status of Stephenson 218 remains forever uncertain, hidden behind the finite speed of light that limits our access to simultaneous information about distant cosmic events. What remains certain is that this star will die violently. The physics governing massive stellar evolution permits no other outcome. The iron core will grow until it exceeds the Chandrasekhar limit and collapses. The collapse will trigger the formation of a neutron star or black hole. The gravitational energy released will drive an explosion that blasts away the stellar envelope. The explosion will scatter enriched material across light years of space, while leaving behind a compact remnant. This fate awaits every red supergiant that has ever existed or will ever exist. The physics operates the same way throughout the observable universe, in distant galaxies as in our own Milky Way. Massive stars burn bright and die young, their deaths enriching their cosmic environments with the heavy elements needed for rocky planets and complex chemistry. The death of Stephenson 218 will be among the most spectacular events to occur in our galaxy during the next million years. It will briefly outshine hundreds of billions of ordinary stars combined. It will produce neutrinos detectable across the entire Milky Way, and possibly in neighboring galaxies. It will create gravitational waves that might be registered by detectors on Earth. It will generate an expanding debris cloud that future astronomers will study for millennia, and it will mark the end of the largest known star in the observable universe, transforming a cosmic giant that could swallow our inner solar system into either a city-sized ball of neutrons or a gravitational abyss from which nothing can escape. The transformation will be complete within seconds during the core collapse phase, though the visible manifestations will unfold over hours to weeks. We are privileged to observe Stephenson 218 during the brief cosmic moment before this destruction occurs. Future observers will know this star only through the remnant it leaves behind and the debris cloud it scatters across surrounding space. The largest known star will become a footnote in astronomical history, its record eventually broken by some newly discovered giant, its death commemorated in the expanding shell of enriched gas that will persist for millennia. Stephenson 218 represents more than an astronomical curiosity or a record holder in cosmic catalogues. The existence of such an extreme object probes fundamental questions about how matter organizes itself under the most extreme conditions nature allows. The largest known star reveals both the capabilities of stellar physics to produce monstrous objects and the limitations that prevent even larger stars from forming. Understanding these limits teaches us something profound about the universe itself. The first limitation relates to stellar birth. Stars form when clouds of gas collapse under their own gravity, a process that has repeated countless trillions of times throughout cosmic history. But this collapse process does not produce arbitrarily massive objects. Nature imposes boundaries that constrain how large a star can grow during its formation. As a protostar accumulates mass from its surrounding cloud, its increasing luminosity generates radiation pressure that pushes against infalling material. The growing star essentially fights against further growth, its own energy output resisting the gravitational attraction, pulling material inward. Eventually, in the most massive forming stars, radiation pressure balances gravitational attraction and terminates further growth. This feedback process limits the maximum initial mass of stars to roughly 150 to 300 solar masses, depending on the metallicity of the gas cloud and other environmental factors. Metallicity refers to the abundance of elements heavier than helium in the gas, which affects how efficiently radiation couples to matter and exerts pressure. Stars more massive than this limit cannot form through normal accretion processes because radiation pressure prevents continued material accumulation before the star reaches higher masses. The forming star literally blows away its own food supply, halting growth at what seems like an arbitrary point but actually reflects fundamental physics. The most massive stars ever observed, objects like R136, a 1 in the Large Magellanic Cloud, weigh in at perhaps 200 to 300 solar masses. These extreme objects live extraordinarily short lives by stellar standards, burning through their fuel in mere millions of years, rather than the billions of years available to Sun-like stars. They represent the upper boundary of what stellar physics permits for initial stellar mass. But initial mass does not translate directly into final size. This distinction proves crucial for understanding why Stephenson 218 holds its record. The most massive stars are not the largest stars. These two categories describe different extremes that peak in different mass ranges. The red supergiant phase that produces the largest stellar dimensions occurs preferentially in stars, with initial masses between roughly 8 and 40 solar masses. Stars more massive than this upper limit evolve differently, often losing their hydrogen envelopes entirely before expanding to red supergiant proportions. Intense stellar winds, driven by their extreme luminosity, strip away the outer layers, exposing the hot, compact interior. These stripped stars become Wolf-Rayet objects, named after the astronomers who first catalogued them in the 19th century. Wolf-Rayet stars are compact and incredibly luminous, but relatively small in physical dimensions, typically only a few solar radii across despite masses exceeding 20 suns. They never achieve the bloated proportions of red supergiants because they lack the hydrogen envelope that would expand during late evolutionary phases. The sweet spot for maximum stellar size appears to lie in the mass range where stars retain their hydrogen envelopes while evolving slowly enough to expand dramatically. Stars around 20 to 40 solar masses occupy this optimal range. They lose mass through stellar winds, but not so rapidly that they become stripped before expanding. They become red supergiants with dimensions measured in thousands of solar radii, like Stephenson 218. Stars less massive than roughly 8 solar masses follow entirely different evolutionary paths that never produce extreme dimensions. These stars, comprising the vast majority of stellar populations, become asymptotic giant branch stars in their late lives. They expand significantly, perhaps to several hundred solar radii, but never approach the dimensions of true red supergiants. After shedding their outer envelopes as planetary nebulae, these intermediate mass stars leave behind white dwarf remnants, dense balls of carbon and oxygen, roughly Earth-sized, but containing masses comparable to our Sun. The evolutionary paths of low and intermediate mass stars simply do not include the red supergiant phase that produces the largest known stellar dimensions. The physical limit on red supergiant size relates to how stellar structure responds to the advanced nuclear burning occurring in the core. As the core contracts and heats through successive burning stages, the envelope responds by expanding. This expansion continues as long as sufficient energy flows outward to support the envelope against gravitational collapse. But this expansion cannot continue indefinitely. Mass loss through stellar winds removes material from the outer envelope progressively over thousands of years. At some point, the remaining envelope mass becomes insufficient to sustain further expansion. The star reaches a maximum size determined by the balance between energy generation in the core and mass loss from the surface. Theoretical models of stellar structure suggest maximum red supergiant radii around 2,500 to 3,000 solar radii for stars with optimal initial masses and mass loss histories. Stephenson 218, at roughly 2,150 solar radii, approaches but does not exceed this theoretical limit. The agreement between observation and theory suggests our understanding of stellar structure captures the essential physics governing these extreme objects. But theoretical limits carry uncertainties that honest scientists must acknowledge. The mass loss rates assumed in stellar models remain imprecise, estimated from observations that themselves carry significant uncertainties. Different prescriptions for mass loss produce different predictions for maximum stellar sizes. The true mass loss rates operating in red supergiants might differ from assumed values in ways that would shift theoretical size limits. The treatment of convection in stellar envelopes involves approximations that may break down in extreme cases. Convection is inherently three-dimensional and turbulent, yet most stellar models treat it using simplified one-dimensional prescriptions. These approximations work reasonably well for ordinary stars, but might fail for the most extended red supergiants where convection operates on scales comparable to the stellar radius itself. Given these uncertainties, the possibility that even larger stars exist cannot be ruled out definitively. Stephenson 218 represents the current observational record, but records exist to be broken, somewhere in the unexplored regions of our galaxy or in distant galaxies beyond current observational reach. Larger stars might await discovery. The ongoing search for extreme stars continues, with increasingly powerful facilities coming online in the current decade and beyond. Ground-based telescopes of unprecedented size will soon begin scientific operations, probing previously inaccessible regions of the Milky Way with resolution and sensitivity far exceeding current capabilities. The extremely large telescope under construction in Chile will feature a primary mirror 39 meters in diameter when completed, roughly 4 times larger than the biggest telescopes currently operating. This enormous light-gathering area, combined with adaptive optics systems that correct for atmospheric distortion, will enable observations of stellar populations hidden behind dust clouds thicker than those obscuring Stephenson 218. The giant Magellan telescope, also under construction in Chile, will combine 7 individual mirrors into an effective aperture of 25 meters. The 30-meter telescope planned for Hawaii will provide similar capabilities in the Northern Hemisphere. Together, these facilities will survey stellar populations throughout the Milky Way with unprecedented detail. Infrared capabilities on these giant telescopes will prove particularly valuable for discovering extreme red supergiants. The same physics that renders Stephenson 218 invisible to optical telescopes applies throughout the dusty regions of our galaxy, where the most massive stars preferentially form. Infrared observations penetrate this dust, revealing stellar populations completely hidden from optical surveys. Space-based facilities will contribute as well, free from the atmospheric absorption and distortion that limit ground-based infrared observations. The James Webb Space Telescope, with its revolutionary infrared sensitivity, has already begun surveying stellar populations in dusty galactic regions. While designed primarily for studying distant galaxies and exoplanet atmospheres, Webb's capabilities extend to detailed observations of evolved stars in our own galaxy. Future space missions currently in planning stages will extend these capabilities further. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey large areas of sky at infrared wavelengths, with sensitivity approaching Webb's but covering far more area. This wide-field capability makes Roman ideal for discovering rare objects like extreme red supergiants that might hide anywhere within accessible survey volumes. The statistical likelihood of finding larger stars than Stephenson 218 depends on how common such objects are and how thoroughly we have surveyed the relevant stellar populations. Red supergiants represent a brief phase in massive stellar evolution, lasting perhaps 100,000 years out of total stellar lifetimes, measured in tens of millions of years. At any given moment, only a small fraction of massive stars exist in this phase. The Milky Way contains perhaps 1 billion stars, massive enough to eventually become red supergiants. If the red supergiant phase lasts 100,000 years and massive stars live 20 million years on average, then roughly 1 in 200 massive stars currently exists as a red supergiant. This suggests roughly 5 million red supergiants populate our galaxy at any given time. We have characterized the sizes of perhaps a few thousand red supergiants with sufficient precision to place them in meaningful size rankings. This represents far less than 1% of the total population. If 5 million red supergiants exist in our galaxy, and we have surveyed only a few thousand in detail, statistical arguments suggest we might be missing the true extremes of the size distribution. Alternatively, Stephenson 218 might represent a true statistical outlier, a rare combination of initial mass loss history, and evolutionary timing that produces dimensions at the very edge of what physics permits. In this case, expanded surveys would find nothing larger because nothing larger exists to find. Only continued observation will resolve this question. Each new survey that fails to discover larger stars strengthens the case that Stephenson 218 sits near the true physical limit. Each discovery of a larger star would demonstrate that the extreme stellar population remains incompletely characterized. The study of extreme stars connects to broader questions about cosmic evolution that extend far beyond individual objects. The elements synthesized in massive stars and distributed by supernova explosions determine the chemical composition of subsequent stellar generations. The enrichment history of the Milky Way reflects the integrated supernova activity over the galaxy's 12 billion year lifetime. When Stephenson 218 eventually explodes, the heavy elements currently being synthesized in its core, along with those produced during the explosion itself, will seed the surrounding interstellar medium. This enriched material will mix with existing gas and dust over millions of years, gradually homogenizing through turbulent motions and differential rotation of the galactic disk. Future stars forming from this enriched material will contain slightly higher abundances of heavy elements than stars forming from unenriched gas. The planets forming around these future stars will incorporate the nucleosynthetic products of Stephenson 218 into their rocky mantles, metallic cores, and potentially their biospheres. The philosophical implications of cosmic scale have occupied human thought since ancient observers first contemplated the nature of the stars. Each generation discovers new extremes that challenge intuition and reframe humanity's cosmic significance. Stephenson 218 continues this tradition, revealing that stars can grow to dimensions that dwarf entire planetary systems. The contemplation of such objects produces a curious mixture of humility and wonder that reflects the dual nature of human cosmic awareness. Humility arises from recognizing how tiny human existence appears against cosmic backdrops. We inhabit one small planet, orbiting one average star in one unremarkable region of one ordinary spiral galaxy, among trillions of galaxies scattered throughout the observable universe. Our Sun measures 865,000 miles across, seemingly enormous by any terrestrial standard. You could fit over 1 million Earths inside its volume, yet a single star exists that exceeds our Sun's diameter by a factor of 2,000, its volume by a factor of 10 billion. The Sun that dominates our sky and provides all the energy supporting life on Earth would be an invisible speck compared to the largest known star. Wonder arises from recognizing that human minds can comprehend these extreme objects despite never directly experiencing them. We have never visited another star. We have never traveled beyond our own solar system. We have never touched the tenuous atmosphere of a red supergiant or felt the warmth of its crimson light. Yet through patient observation and mathematical analysis, we have determined the properties of objects 20,000 light-years distant with remarkable precision. This capacity for remote understanding represents one of humanity's most remarkable achievements. We measure distances using subtle angular shifts in stellar positions as Earth orbits the Sun. We determine temperatures from the colors of light that stars emit. We calculate masses from the orbital motions of companion objects. We infer sizes from the relationship between brightness and temperature. Each of these techniques required generations of scientists building on previous work, refining methods, improving instruments, and testing predictions against observations. The infrared observations revealing Stephenson 2.18 required semiconductor physics developed in the 20th century, optical engineering refined over decades, and computational capabilities that would have seemed magical to scientists just a century ago. The technology enabling cosmic understanding represents accumulated human achievement across centuries of effort. Each telescope builds upon lessons learned from previous instruments. Each detector incorporates improvements suggested by earlier observations. Each analytical technique refines methods developed by previous generations. The current state of astronomical knowledge represents the cumulative effort of thousands of scientists working over hundreds of years. This technological progression shows no signs of slowing despite the remarkable achievements already accomplished. Future facilities will achieve sensitivities and resolutions exceeding current capabilities by factors of 10 or more. The cosmic census will expand to include objects currently invisible to our instruments. Phenomena we cannot currently detect will become routine observations for future astronomers. Consider the progression of cosmic awareness over just the past 4 centuries. When Galileo first turned a telescope toward the sky in 1609, he discovered moons orbiting Jupiter and phases of Venus that proved Earth was not the cosmic center. Within a generation, the heliocentric model became scientific consensus, displacing thousands of years of geocentric assumption. Over subsequent centuries, astronomers discovered that the Sun is one star among many, that stars are distant suns, that the Milky Way is a galaxy containing billions of stars, that other galaxies exist beyond our own, that the universe is expanding, that cosmic expansion is accelerating. Each discovery extended human awareness to larger scales and revealed new phenomena invisible to previous generations. Stephenson 2.18 fits within this progression as the current boundary of our knowledge about stellar dimensions. Future discoveries may extend this boundary or confirm it, but either outcome will add to human understanding. The timeline of human cosmic awareness spans barely 4 centuries since the invention of the astronomical telescope. In that brief interval, we have progressed from believing Earth occupied the cosmic center to mapping the large-scale structure of the observable universe, spanning billions of light-years. We have discovered that our Sun is one star among 400 billion in our galaxy, that our galaxy is one among 2 trillion in the observable universe, that the observable universe may be an infinitesimal fraction of total cosmic reality. The rate of discovery continues accelerating as observational capabilities improve. More astronomical knowledge has been generated in the past 50 years than in all previous human history combined. The next 50 years will likely see comparable or greater advances as new facilities come online and new techniques mature. The personal relevance of such cosmic knowledge varies among individuals in ways that reflect diverse human perspectives on meaning and significance. Some find comfort in placing human concerns within larger contexts, recognizing that earthly problems appear insignificant against cosmic backdrops. The anxieties and conflicts that dominate human attention seem less consequential when viewed against the scale of stellar evolution and galactic dynamics. Others find such perspectives alienating rather than comforting, preferring to focus on scales where human action matters and human relationships provide meaning. The knowledge that stars can grow to monstrous dimensions does not help solve problems of poverty, disease, conflict, or environmental degradation that demand human attention. Neither response is incorrect. Cosmic knowledge serves multiple purposes for different individuals and need not serve the same purpose for everyone. The universe does not prescribe how humans should respond to knowledge of its scale. That response remains a matter of individual choice, shaped by personal values and circumstances. What remains objectively true regardless of individual response is that Stephenson 218 exists. 20,000 light-years from Earth, embedded in a cluster of red supergiants, burning with the power of hundreds of thousands of suns, spanning distances that would swallow most of our solar system, this star represents an extreme of cosmic possibility that actually occurs in nature. This is not speculation or theoretical extrapolation, but confirmed observational fact. Multiple independent measurements using different techniques converge on the same basic conclusion. The largest known star in the observable universe burns tonight, invisible to human eyes, but revealed through infrared telescopes that see through the intervening dust. The light we observe tonight departed this star around the time human ancestors first crossed the land bridge into the Western Hemisphere, roughly 20,000 years ago. Those photons travelled across interstellar space at the fastest speed the universe permits, passed through dust clouds that blocked most of their companions, and finally reached telescopes that recorded their presence. Each photon carries information about conditions in the stellar atmosphere 20,000 years ago. The star we observe is not the star as it exists today, but as it existed during the last ice age. We look backward through time across a span longer than recorded human history, witnessing a cosmic past preserved in ancient light. In the grand cosmic inventory, Stephenson 218 is merely one star among hundreds of billions in our galaxy, which is merely one galaxy among trillions in the observable universe. The star's mass represents roughly 15 to 25 solar masses, trivial compared to galactic masses measured in hundreds of billions of solar masses. Its physical extent, while enormous by stellar standards, spans a negligible fraction of the distances separating stars. Yet this particular star holds a distinction that sets it apart from all others we have found. It is the largest. This simple superlative, the single word largest applied to a single object among the trillions of objects in the observable universe, captures something profound about where this star sits within the cosmic hierarchy. Records carry psychological weight that transcends their literal meaning. The tallest mountain, the deepest ocean, the largest star. These extremes define boundaries of possibility. They mark the edges of what nature permits under the physical laws governing our universe. The largest known star reminds us that the universe permits extremes beyond ordinary imagination. Somewhere in the Milky Way, obscured by 20,000 light-years of cosmic dust, a star exists that could swallow our entire inner solar system, including the orbits of Mercury, Venus, Earth, Mars, and Jupiter. This is not speculation or science fiction, but confirmed observational fact. The cosmos really does produce such monsters, and we, brief creatures on a small rocky planet, have figured this out. We have measured the size of an object we will never visit, never touch, never experience directly, except through the faint infrared light that reaches our telescopes after a 20,000-year journey. We have extended human knowledge to encompass extremes that our ancestors could never have imagined. We have discovered, through patience and ingenuity, and accumulated technological capability developed over centuries, that stars can grow to dimensions spanning billions of miles, containing volumes billions of times larger than our Sun. This understanding did not exist a century ago. It exists now because humans chose to build telescopes, develop theories, and dedicate resources to cosmic exploration. This discovery matters, even though it does not change daily life on Earth, does not solve practical problems facing human civilization, does not cure diseases or prevent wars or reverse environmental damage. It matters because it expands what humanity knows about the nature of reality. It matters because understanding is valuable, independent of practical application. It matters because we are creatures that seek to know our cosmic context. Stephenson 218 will eventually die in one of the most spectacular events our galaxy will witness over the next million years. But for now, it burns. The largest known star in the observable universe continues converting matter into energy at rates hundreds of thousands of times exceeding our Sun. It continues shedding material into surrounding space through powerful stellar winds. It continues evolving toward eventual catastrophic collapse. We observe it from 20,000 light-years away, reconstructing its properties from ancient photons, marveling at the scale of what nature produces when given sufficient matter and sufficient time and the right physical conditions. The cosmos contains wonders beyond counting. Stephenson 218 is one of them, a star so vast that comprehending its true dimensions requires abandoning all terrestrial intuitions about size and scale. The largest known star burns tonight, and we have measured its dimensions, predicted its fate, and placed it within our understanding of how stars live and die. This achievement, however modest compared to cosmic scales, represents something significant in the universe's long history. Matter has organized itself into forms capable of understanding its own extremes. Atoms that were once part of ancient stars have assembled into beings that can measure the largest stars now burning. The universe has become aware of itself through creatures living on a small planet, orbiting an ordinary star in an unremarkable corner of an average galaxy. That awareness extends now to encompass Stephenson 218, the largest known star in the observable universe. We know it exists. We know how large it is. We know how it formed and how it will die. We know its place within the cosmic hierarchy of stellar objects, and knowing these things, we are connected to this distant giant in ways that transcend the physical separation of 20,000 light-years. The same physics governing Stephenson 218 governs our Sun. The same elements comprising that star comprise our bodies. The same cosmic evolution that produced that monster produced the planet we inhabit. We are all part of the same universe, subject to the same physical laws, participating in the same ongoing cosmic story. The largest known star and the smallest observers are connected through the fundamental unity of physical reality. That connection makes the existence of Stephenson 218 personally relevant to every human being alive today. Not because the star affects our daily lives, but because understanding it extends our conception of what reality contains. The universe is stranger and more extreme than everyday experience suggests. Stars can grow to dimensions that swallow solar systems. The largest known star burns tonight. We have found it. We have measured it. We have understood it as well as current science permits. And in doing so, we have extended the reach of human awareness to encompass one more wonder in a cosmos filled with wonders beyond counting.